Hello, welcome everyone to this third video on the series of basics of material testing. Today we are going to talk about a very interesting topic known as indentation plastometry using i3D. The last two videos we spoke about how material properties can be determined. We talked about the first method where we used the industry standard way of doing mechanical testing, which was called as the tensile testing. The second, faster and quicker way using an indentation based procedure, we call this as hardness testing. And the third, what we talk about today, is a very novel method which was developed here at Imprintec about 10 years back. It's called as indentation plastometry using i3D. Let's first understand what the term indentation plastometry means. Indentation plastometry is a test method which uses an indentation based procedure to determine plastic stress strain properties. Let's break this word down into two parts. The first part is the indentation, which is very similar to how you did hardness testing. That is, you have a very sharp indenter tip and we drive it into a material. The material deforms plastically, right? And the residual plastic deformation that is left out is what is called as plastometry. Imprintec back in 2019 described this whole procedure in a standardized way. First time, this is now described in the DIN SPEC 4864. DIN stands for the German National Standard. It's not a standard, but it's rather a specification, so it's more of a guideline of how you could apply this procedure. Back in 2025, last year, in the end of the year, we received the ASTM international standard for this procedure. It is ASTM E3499. So this method is now globally recognized and standardized now. What is indentation plastometry using Imprintec's i3D method? And what does the term i3D stand for? The I in the i3D stands for indentation, and 3D stands for 3D optical measurement. We'll describe to you why. Because this whole indentation plastometry has basically three important steps. And the first step is indentation. The second step is 3D measurement, and the third step is inverse finite element procedure in combination with iterative optimization. Let us first understand all of these steps. The first step is indentation. So we have a metallic material below or a metallic specimen below, very similar to hardness testing. You have a sharp indenter, you bring it down with a certain force. That creates a sort of a plastic deformation on the material. This plastic deformation is recorded using a 3D optical measurement system. What is the importance of this plastic deformation? Every material deforms under the load very uniquely. Let's say very similar to how a human fingerprint is unique to the human being. Similarly, the plastic deformation of a material is very unique to the material. This is recorded using a 3D system, and we use this information and base out of that we have digital twin models behind. I will talk about all of these steps in detail. We have a digital twin model behind, and using an inverse finite element procedure, we are able to determine the mechanical properties. So let's break it down step by step. Imagine this piece of clay that I hold in my hand to be a metallic material, and this pen I have, or stylus, to be an indenter tip. So I press this into the material, you see it creates a deformation zone in the material, that is, it plastically deforms, that there is a permanent deformation on this material. We are able to scan this using a optical scanner. Similarly, we are able to create the same procedure using computer models. So we create using a computer model what we call as finite element simulations. We create digital twins. Now, using these digital twins and combination with an iterative optimization algorithm, we are able to determine mechanical properties. To understand this further, let's understand what is an inverse method, but in the beginning, let's understand what is a forward method. Then we can understand what is the backward or the inverse method. The normal way of creating a digital twin so it's a method of actually creating a digital twin here. So this is how you would create a digital twin. That is, you have certain inputs, that is, you know the material properties, let's say, you know the force that you apply, and you know a shape of the indenter. You put this into a finite element model, and the output of this model or the simulation, the computer model, will give you some plastic deformation. That is your plastic deformation geometry. Now look at it from the other way around. That is, you have experimentally a plastic deformation, what you are able to record using a 3D sensor. So that is from this thing. You have an iterative optimization procedure where it can change some input parameters in the digital twin, and what it's trying to do is, let's consider this residual indentation geometry in terms of a profile, and what it essentially does is the iterative solver tries to match which digital twin matches our experiment. So, for example, the first iteration may not match so much. The second iteration might be slightly bit better, but also does not match. But on continuous iteration, we will find match which is very good and very close to our experiment, which is the black curve. And once we find out that becomes our selected curve, or the digital twin is formed. Since we know what properties, so we know all of these properties, what we use to create the digital twin. From the experimental side, once the digital twin is found, we can determine its properties. So it's the other way around. So you were going input, which were the properties. You were creating the digital twins. Experiment, we are getting the geometry and checking which digital twin matches. Right? We are looking at different digital twins which match this using the iterative procedure. This is called as the inverse method. This is what is the core of our algorithm, which is based out of mathematical optimization and AI-based optimization as well. And together they're able to provide these results really fast and really accurately. What are the advantages of this method? Similar to hardness testing, it's fast, it's cheap, but unlike hardness testing, where we are only using conversion values, since we are getting very detailed geometrical information, we get information which are actually mechanical properties which are very similar to tensile properties. But at the same time, it being localized, flexible, and almost fifth one, almost non-destructive. Thank you everyone for joining back on this video, and see you all the next time. Thank you.